Okay, we'll begin with some examples of so we have seen that if we apply the theorem that we have proved yesterday, then these spaces with the usual metric, these spaces with the metrics that we have seen, I mean, I am not Sn, Hn are all simply connected constant curvature spaces which are complete. So they are all symmetric spaces. But to prove that these are symmetric spaces, we can directly produce symmetries. Okay. So these are all symmetric spaces, but we can produce, but we need not appeal to theorems that we have proved yesterday. We can directly prove that these are symmetric spaces by explicitly constructing symmetries. So Rn, for example, if you take a point P, then you define sigma P. So you just have this P and you just reflect along. So you have the point here, so reflect here, or here, reflect here, or here, reflect here. So the formula is going to be, so you know what to do at origin, but you just translate it by a vector at the point P. So, for example, so we know that at 0 it should be minus V, and then we also know how to produce that I'm going to talk later, but you know, this LP minus P, and that is going to give you sigma P. And if you recall, if you write down the formula explicitly, you will see that it is going to P minus V for all V. And you can check that this is a symmetry. And now, so this is isometry, because if you write down, it is going to be sigma P of V is going to be 2. So P minus P plus V. So okay. So it is going to be 2P minus V for all V in Rn. And that is going to be a translation along with an element in On. So this is 2P, it's a 2P, and minus of V is an element in the orthogonal group. So isometries of Rn, so recall that isometry group of Rn, it is the semi-direct product of On, okay? And it acts by x going to x plus b. A is in On, B is in Rn. So this is a map of this form. So this is an isometry, and this does the job. All right, now Sn is x in Rn plus 1, norm of x is 1. And so for Sn, what I do is I take a vector V in the sphere, and I take the orthogonal plane orthogonal to this, and I take the reflection which fixes V, and you know, it sends this vector to the other vector. So it sends negative V goes to its negative in the orthogonal plane perpendicular to V. So that's a reflection, and if you restrict that reflection to Sn, you get an isometry, and that isometry is going to do the job. Okay. So if you write down the formula, sigma P of V is going to be 2, let's call it P, 2 P V P minus V. Okay, and the fact that norm P is 1 is going to tell you that this is a reflection, and this is of course an orthogonal element in ON, so, and this is going to do the job. Okay, it's going to keep P fixed and P and the antibodal point fixed, and send every geodesic to its, it is a geodesic symmetry. Similarly for Hn, so Hn, the model that I'm going to choose is the hyperboloid model. So I have this form in, so xy is in Rn plus 1. So I consider this quadratic form, which is xi yi minus xn plus 1 yn plus 1, I is equal to 1 to n. So, and you take the, so my Hn is going to be x in Rn plus 1, x, let's denote this by n1, this is a signature n1 form, and this is going to be n1 is equal to minus 1, and xn plus 1 is greater than 0. And I ignored the lower half, so I consider this one to be Hn, and again, and the isometric group here is elements in ON1 for which so these are linear transformations, so it either it flips, so I'm considering those which keeps this piece invariant. Okay. Okay, so isometry of Hn is this. So its connected component is connected component of SON1. But this is so this is an index 2 subgroup in ON1. Okay, it is not SON1. So this keeps this one fixed. So there is a subtle difference between SON1 and N1. Okay, so and this you can check that I am also again going to give a reflex element here, and this needs some little bit of checking, which you can do. That this is a element in the which keeps the form invariant, which I'm going to write now. So 2 Vp and 1 P minus V. Okay, so you can check by direct calculation that this keeps the form invariant and this does the job. Okay, so without appealing to previous classes theorems, we can directly prove that these spaces are isometric, Riemannian isometric spaces. Okay, so now there is a very important example. So if I take a connected compact Lie group, you can give a symmetric space structure to it. Let G be a compact connected Lie group, then I'm going to put a metric using which I can give a symmetric spec structure. So what is a metric? So I choose any metric that I like on, so choose any inner product on the tangent space at identity, and the tangent space, on the tangent space the group acts by adjoint representation, okay? So add G is the differential of CG at E, CG is the conjugation by G. So it clearly fixes, this CG clearly fixes identity, and if you take the derivative, it belongs to GL of TEG. So every Lie group has a natural representation this way to GL, sorry, TEG, G going to add G, and I take this adjoint representation in this case, and the fact that G is compact, it has, the Haar measure is finite, so I can average, starting with any inner product, I can average this inner product, and I produce a new inner product by this way, and the way, since I have already, since the measure is left invariant, so this inner product is going to be add invariant. So I'll say old, and since I'm going to use this all the time, I don't write anything here. So this inner product has the property that at Gx, at Gy is xy, okay, for all xy. Okay, now what I do is I translate the inner product to every other tangent space because I'm in a Lie group and I have the left translation. So I define, so this is defined to be this one for all xy in TEG, and at G is I G y tilde x tilde y tilde. I'm simply translating the inner product with respect to this is the only choice. I mean, if you are asked to produce, you're given just a compact group, and everybody will see that this is the, I mean, this is following your, basic instinct. Okay. So this is, by definition, this is a left invariant inner product, and I consider this inner product, and with respect to this, I'm going to show that this is a symmetric space. So since the whole group acts as transitively by left translation on the group as isometries, I'm just going to produce a symmetry at identity. But before this, I could have just started, I mean, I need not have started with the inner product which is invariant, but I chose this inner product so that my right translations are also going to be isometries. Okay. So in general, if you take a Lie group, and you can just give a left invariant metric using these left translations. Just choose the inner product and translate it. But I'm choosing a add invariant metric to show that this inner product is also right invariant. Okay, so this is an exercise. So we know by construction that LG is in isometric G, and by this fact, by this property, RG, the right translations are also isometrics. I'm going to need this in order to prove that certain map is an isometry on the whole group. So I define now sigma G to be G inverse. Okay. So what does it do? It fixes identity. Okay. And this is also true that D sigma E is minus identity. Right? Because sigma Tx is, this is the Lie group exponential map. This becomes exponential minus Tx, and this is why I have this. Multiplying by minus 1 in any inner product space is an isometry. So this is a linear isometry. Okay. But I need to check that this is not just a linear isometry at the tangent space at identity, but it is a linear isometry everywhere. So this is where I require the fact that this RG is also. So you'll see that so sigma LG of X, what is it? A simple calculation says that this is GX inverse. So this is X inverse G inverse. So this is sigma, yeah. So this is R G inverse sigma X. So this is sigma LG is R G inverse sigma. And I have the chain rule for derivative, and this says that, this at G dLG at identity is dr G inverse at the appropriate point, and this sigma identity. So what does it say? I know that this is a linear isometry. I know this is a linear isometry, and just now seen that this is a linear isometry. So this becomes a linear isometry. So this says that sigma G is an isometry. Okay? And this proves the fact that any compact Lie group is a symmetric space. Okay? So all these examples are like, except all these examples that I have drawn are simply connected examples of symmetric spaces. But you can take a non-simply connected compact Lie group and produce a symmetric space out of it. By the way, if the symmetric space that we are going to see, the theory leads us to say that, symmetric spaces are intimately connected with Lie groups. We will see that for a most general construction of symmetric spaces. And we'll see that there are three types of symmetric spaces. One is Euclidean type, one is compact type, and one is non-compact type. And the symmetric spaces, the simply connected symmetric space can be written as direct product of symmetric spaces of this type. And so if I take a non-compactite symmetric space, it's always going to be simply connected, and it is going to be in fact homeomorphic to Rn. Okay? So if you want to produce a non-simply connected symmetric space, we have to only look for compact examples. So here is an example of a compact group. If you choose any compact group that you like, which is non-simply connected, and that compact group has a symmetric structure. Okay, so let me just point out the fact that the symmetries, since in a symmetric space, the full isometric group, okay, so acts transitively, we have seen. If we can produce symmetry at one point, we know symmetry everywhere, okay? Because if I know symmetry at P, and if I want to produce a symmetry at P naught, I just take a isometric, an element which takes this point P to the point Q, okay, an isometry, and just conjugate that that symmetry at P by this. So basically, sigma P, sigma inverse, sigma, this is going to give you a symmetry. So you just need to produce, if you want to produce symmetry for every point, you just need to produce symmetry for one point. Okay. And secondly, in a symmetric space, in the case of Sn, you see that it fixes, any symmetry fixes 2 points, the symmetry that I produced. So the fixed point set of symmetry is 2 points. In case of non-compact type, the fixed point set is going to be singleton. But in case of compact type, the symmetric space may have other, the fixed point set may not be discrete. So you can give an example. So just take a compact Lie group. So what are the fixed points of the symmetry? Sigma, we have produced a symmetry G going to G inverse. So fixed point set elements are just order 2 elements, right? So in the example of compact Lie group, okay, I mean, you can produce a compact Lie group for which this is not a discrete set. So for example, you can choose a compact Lie group. So how to get a square to such an element? You take something called a maximal torus, and once you given a maximal torus is just a product of copies of circles. You can choose an element which is non-central and which is square 2. Okay, so choose which is not in the center and 2. So you take the conjugacy class, and it will have a, the conjugacy class will contain a submanifold of positive dimension. So the fixed point set is going to contain a submanifold. So it is, although it is fixing this identity is an isolated fixed point, but this is no need to assume that the fixed point set is always discrete. Okay, and such an example is possible only in the compact case. All right. So now I'm going to give the most general construction of symmetric spaces, and I'm going to introduce the Riemannian symmetric pair. And so, Oh, G square is equal to 2. I'm sorry. Thanks. G square is, yeah. Maximal torus in a compact group is the, so what is a torus? Torus is a product of copies of S1, S1 cross S1. S1 is a compact Lie group, circle group. S1 cross S1 cross S1 cross S1 is called a torus. So any compact Lie group has a subgroup which is of this type. Okay? and you consider the maximal one, they're all conjugate. Any element lies inside a maximal torus. So all I'm saying is how does one produce a square two element? Because in S1 we know how to produce. So we know in S1 cross S1 cross S1. To produce a non-central element, you just look at maximal torus, and for example, you take -1 in some coordinates and 1 1 1 in other coordinates. That's likely to be non-central. Okay. So, all right. So, Riemannian. Just let me see my list where I'm going. Yeah. Riemannian symmetric pair. Well, it contains 4 elements, although it is called pair. So, G, K, sigma, I'm going to write down what are they, is called a pair if G is a connected Lie group, sigma is in ought of G, a smooth homomorphism of order 2, K is a closed subgroup of the form G sigma naught. What is G sigma naught? So what is G sigma? G sigma is the fixed point set. So X in G, so that's sigma, sorry, G in G, so that sigma G is G. So K is a subgroup in between the fixed point set and its connected component. Add K. So I have this adjoint representation which I introduced in the just a few minutes back. So add K inside GL TEG is a compact subgroup. And let me explain what P is. So P is X in TEG, so that D sigma E at X is minus X. So it's a subspace of the Lie algebra, which is the eigenspace, negative -1 eigenspace corresponding to this order 2 automorphism of the Lie group. And this on P is a add K invariant. Yeah, so I should say, okay, a remark is, so this is an automorphism of order 2. So the D sigma, the derivative, is an automorphism of the Lie algebra. And since original automorphism of order 2, so is the derivative. And so the possible eigenvalues are 1 and -1. And it has to have -1 eigenspace because I'm assuming order 2. If it has only 1 eigenspace, then it is order 1. But assuming order 2, so this is certainly non-trivial. And so it is a very easy fact to prove that this add K keeps this P invariant. And okay, so and that follows from the fact that K is here. Okay, so this is an Adk invariant space, invariant inner product. Okay, so I'm given this data, and this is called a Riemannian symmetric pair. Although this has 4 elements, we call it a pair. If we have such a thing, so out of such a data, I'm going to produce a Riemannian symmetric space, and we'll see next that every Riemannian symmetric space appear from this data. Okay. Huh? G sigma is fixed point. G sigma naught is a connected component of the fixed point. Okay. So how does one produce from a Riemannian symmetric space from this data? So the manifold that I'm going to take is going to be the space of left cosets of G in K. So we know that this is a closed subgroup. K is a closed subgroup. A closed subgroup. Yeah, in fact, any subgroup is going to be closed, but any subgroup in between this is going to be closed because G by G naught is discrete. And all right. So this is the, we have seen, we know, I'm assuming a fact which is not so trivial to prove that we know. So we assume that G mod K has a manifold structure. And that is true for any group and any closed subgroup. In fact, in more fancy language, it is G over G mod K is a K principal bundle over G mod K. That is, given any neighborhood of G mod K, given any point in G mod K, you can find a neighborhood which is going to look like neighborhood in G mod K, so that this pi inverse is going to look like U times K, okay? And this to U, and the first projection, this diagram commutes. Okay, these are very general facts about Lie groups. You can find in any basic Lie theory book, will more or less contain the proof of this. I'm going to assume this thing, and so my underlying manifold is G mod K, and I have this projection called, sending G to the left coset, okay? So I have this G, GK. So I have this I have a distinguished coset containing the identity, I call it EK, and I have this map D pi E, and I have this map, these are inclusions, and this sequence is exact. That means at the tangent level I have, of course, a map which is surjective, and the kernel is precisely K. Okay? So if I take any complement of TEK inside TEG, let's say any complement, this is going to give me an isomorphism of the vector spaces. So my K is TEK here, and my P is a complement. So I put P here, and I consider this d pi e, and this is an isomorphism of vector spaces. Okay. I have an inner product here. I'm given an inner product which is at k invariant. So I transport that inner product to an inner product at the tangent space at identity. Okay, via this map. Transport. So I am given a manifold now, and I give a distinguished point Ek. Now I have an inner product at Ek. Now I know that this group acts on Gk by left translation. So Lg of xk is defined to be Gxk, and these are all diffeomorphisms for all G, and this is a transitive action. G acts transitively. So I take any other Gk I have Tek G mod k. I have this map DLG Ek. So I have an inner product here. I have an inner, so I transport that inner product at Gk. But the point here is there is no unique Lg by which I can, so Lg, and there is not necessarily, this may vary by, so there is no unique left translation which sends Ek to Gk. Okay? So this assignment on the face of it doesn't look like a well-defined process. But this is going to be well-defined because of the fact that this inner product at P is at K invariant. Okay? So I'll ask you to check that this is well-defined, because so this assignment of assigning inner product to Gk is a well-defined process. There is no confusion. This is because this process is okay, because so since this P is at K invariant, this Ek at Ek, see my group K acts on, there is a representation of GL of Tek G mod K. Because Lk keeps the point fixed, the derivative Lk gives me a representation of K inside. So K acts on P, K acts on Tek G mod K, and this map that I've given, this is a K equivalent map. Okay? So K acts on this by add, K acts on this by simply taking the derivative of Lg, and this map d pi is going to be K equivalent map. That's very easy to check. Okay? So I have an inner product which is at K invariant, so I obtain an inner product which is Lk invariant. Okay? Once I have that, then I transport this to other points, there is no confusion. Okay? All right. So I have assigned so I made a inner product, I have assigned to every point in G mod K, I have given an inner product. Is it smooth? It's smooth because it is Lg invariant, G invariant. Anything which is a group is acting transitively on a space, and if the thing is G invariant, it is likely to be smooth. And you can take it as an exercise that this is a Riemannian, this G mod K is a Riemannian manifold with respect to this inner product. Okay. So prove that this assignment of inner product GK on GK makes GK a Riemannian manifold. Okay, so some smoothness condition has to be checked, and that will follow from the property that the G is a Lie group and G is, it simply will follow from the property that G is a Lie group, by which I mean that G cross G to G, the product map is smooth. This is going to follow from that. Okay, so now what is a symmetry? So symmetry is going to be given by this sigma that I started with. So I define now a map from G mod K to G mod K, which is given by sigma of x k is defined to be sigma of x. Okay? I mean, these are the obvious guesses that one would make. And the fact that, so this is an exercise. So since d sigma on P is acting by multiplying by -1, this d sigma bar, so since d sigma P of x is -x when x is in P, it will imply that d sigma bar at Ek is minus identity. Okay? And this is a map again, any minus identity is always an orthogonal element with respect to an inner product. So this map, by the way, this is a diffeomorphism, there is no confusion about it. Okay? This map is very easily, you can prove that this is a diffeomorphism because G to G, sigma, G mod K, the diagram commutes. So this map is a diffeomorphism, and so this map is d sigma bar Ek is from T K G mod K itself is a linear isometry. Okay, and since left translations, so left translations are isometry by the definition. The way the inner product is constructed, left translations are isometry. Since LG, so since G acts on G mod K transitively by an argument which is similar to the case of compact groups, d sigma G, d sigma is in isometry of. Okay, and since d sigma at identity it is -1, it is an isolated, Ek is an isolated isometry, isolated fixed point. Okay, since this is an isometry, so I have produced. I know that G acts transitively on G mod K, and I have produced a reflection at identity at the point Ek. So by the remark that I made before, you can get the isometry at every other point. Okay? So this is a symmetric space, and every other symmetric space is going to look like this. So let me prove the converse. And so any Riemannian symmetric pair gives rise to a symmetric space. And now I'm going to prove that any symmetric space is going to come as a Riemannian symmetric pair. Okay? So I need some major theorems in Riemannian geometry. So this is something very general before I go into other details. So I consider any Riemannian manifold, M, B, any Riemannian manifold. I consider the group of isometries. This is just an abstract group to start with, okay? We don't know anything about it. But we can put a topology on it so that it will not just become a topological group, it will become a Lie group. So this is a result of Steenrod and Mayers. So let me just put a topology. So this is called compact open topology. So CU. So let C be a compact set and U be an open set. Then I consider maps F from, or maybe F in isometry M to M, for which the compact set is taken to U. Okay, so this is just a set, and this is going to be subbase for a topology if I vary compact set and open sets. And with respect to topology, the major result in geometry is proven by Steenrod and Mayers, which says that the following, that isometry M is a Lie group with respect to this topology, so that the map, the natural action, this map is smooth. Okay, this is number one. Number two, so isometry, so given M, I consider the bundle of orthogonal frames. So then let O M be the bundle of orthonormal frames over M. So this is a ONR bundle, principal bundle. And if I choose any point E in this OM, then the isometry acts on OM by, so it takes a base to another base or another point. Okay, I choose orthonormal base on the tangent space of a certain point, fix a point and take a base, and then I take an element by D of that element, it takes to another orthonormal base because this is an isometry. Okay, so isometry embeds inside OM this maps G going to G. Let's call it a base B. B is an embedding. So this is embedding, the image is a regular submanifold of OM by this embedding. Okay. So these are the results, which is standard result. And this, the second fact says that, fibers are compact. So there is a corollary of the second fact which says, so fibers of this space is homeomorphic to ONR. Okay, so this is a compact thing. Pivots are compact. So if I take fixed point of this, so corollary is, so let M be a point in M, then stabilizer of M inside isometry M is a compact subgroup. Okay. Okay, so this is a gadget I'm going to assume and produce a symmetric space, so it's a Riemannian symmetric pair out of a symmetric space. So I consider a symmetric space, and the isometric group is going to be a Lie group. So now let M be a symmetric space. I consider isometry M. This is a Lie group. So let G, no, not G. So this is a Lie group. And I denote G by the connected component of this Lie group. Okay. The full isometric group, we have proved that it acts transitively on the manifold, and so will its connected component. So here is an exercise. Suppose G is a group acting on a manifold smoothly. Suppose G acts transitively, then so does its connected component G naught. Okay? Huh? M is connected. Right. Absolutely. Yeah. M is connected. This I'm just giving an idea of this. You can just see that G this M is going to be diffeomorphic to G mod, the stabilizer of a point P. So the orbit map G going to M, G going to GP is an open map because this is diffeomorphism, and G by stabilizer P, the orbit map is an open map. Coset map is an open map. That is very easy to see. So here is an open map, and that's the proof. Okay. And that will this is an open map, and that will show you that the connected component acts transitively. Okay, so my G here is the connected component of the isometries. And what is K? K here is K here. So I fix a point now. I fix a point. So I fix a point M naught in M, and K be the stabilizer of M naught intersection G. Okay. So of course, G mod K to M, the orbit map that G M naught is diffeo. Okay. Okay. So I have produced a Lie group, and K is a compact subgroup of G because of this result. And now I'm going to all right, so what is sigma? So I have to get automorphism inside order 2 inside this group, and that I'm going to produce from the symmetry that I get. So let SP in isometry M be the symmetry, because this is a symmetric space. I consider that unique symmetry at the point, not P, not M naught, at M naught. S is in isometry M, not necessarily in the connected component, but the connected component is normal. Okay, so I consider the conjugation. So S is an order 2 element. Order of S is 2, and I consider the conjugation of by Sm naught from G2 itself. Okay. G is connected component of the group, so it is normal. So the conjugation, since Sm naught is order 2 element, so is the conjugation. Okay. So I need to say that I have this G sigma now. So sigma is the conjugation by this, is the conjugation by Sm naught. So I need to prove this. Okay. So I need to prove the stabilizer of M naught is commuting with Sm naught. I take any isometry which fixes M naught, it commutes with M naught. Sorry, it commutes with Sm naught. Okay. So I take phi in K. That means phi of M0 is M0. I need to prove that phi gets fixed by conjugation by Sm naught, and that is equivalent to saying that phi commutes with Sm naught. And I consider Sm naught inverse. Note that this M naught is same as M naught because Sm naught fixes M naught, phi fixes M naught. So here is an isometry which fixes M naught, and the derivative is the derivative of phi because the derivative of Sm naught is identity, minus identity. So minus identity, minus identity. So I have an isometry. So I have two isometries for which fixing M naught and the derivative is equal. So the isometries are equal. So this says okay, so because d of this at M naught is same as d of phi at, so d of this at M naught is this at phi at. Okay, so these are properties of isometries. Okay. So this part is done. And this part is proof is also very nice. So I take, so what do I need to prove in order to prove that this connected component lies here? So I take an element in the Lie algebra of this sigma x naught. I want to prove, so a connected group is generated by the image of the exponential map, right? So to prove that this is here, enough to prove that XTX lies in K for all T is in R. Okay. But these are isometries. Okay. And so this is an isometry, and the fixed point set of sigma, it is an isometry that is commuting with sigma, right? Because conjugation by S sig. So this is an isometry here, right? So we know that sigma of XTX is XTX. So these are isometries which are commuting with, so this is a one parameter family of isometries which is commuting with SM naught. So if I consider the fixed point set of SM naught, this one parameter family of isometries keeps the fixed point set invariant, right? Because it is commuting. But the point is that M naught is an isolated fixed point of SM naught. So I have a connected one parameter family of isometries which is acting on a set, and that set has an isolated point. What does it mean? That means this whole one parameter family of isometries fixes that point, because that M naught is an isometry. M naught is a fixed point, sorry, isolated point. So this implies M naught, so this implies. Okay, so these are very nice bunch of arguments which says that, you know, so this is the only nice point about the entire proof. Huh? No, exponential math, the image generates the whole group. It is certainly not surjective, but the image contains an open set, and any open set in a connected Lie group generates the whole group. Okay? All right. Okay, so yeah, so, and what do I have to prove now? I have to give you a inner product which is add K invariant and so on. So pull back. So I have this G mod K to M. It's a diffeomorphism, and at EK going to that preferred point that I started with, M naught. And this diffeomorphism, I have an inner product from the Riemannian metric. I pull back. So yeah, so since sigma, so since this is an automorphism of the group which is keeping K invariant, the complement of K, the negative, so what I'm saying is this P, so let it is just the same as before, let P be X, so that D sigma of X is minus X, okay? And just pull back the inner product on P, so this P sits inside, so P, the inclusion of TG gives me an isomorphism, so from TG to d pi E gives me an isomorphism. So this is an isomorphism, and pull back the inner product via, because we are already given an inner product on M at M naught, and that will do the job. So what I have shown you, that any Riemannian symmetric space gives rise to a symmetric pair, and conversely any symmetric pair gives me a Riemannian symmetric space. So On one hand, I have Riemannian symmetric pair. On the other hand, I have Riemannian symmetric spaces. And I have a process to go from one to another. So I start with a Riemannian symmetric pair, consider a symmetric space out of by this construction. And again, I consider the Riemannian symmetric pair of that symmetric space. Do I get back the Riemannian symmetric pair? No, we don't get back. Okay? But the other side process, I'll tell you why. Other side process is, so I start with the symmetric space and consider the Riemannian symmetric pair. Then I construct the symmetric space. From the Riemannian symmetric pair, I get back the symmetric space. Okay? So why? So this kind of complication will arise only if we consider the case of flat metric, like Euclidean metric. Okay, this is not going to arise in the case of semi-simple symmetric spaces, but this is going to. So I'm just going to give you an example of this process. So I consider SON. Okay. I consider a proper subgroup of SON. Okay. And I consider let's call it G, H. I consider H. H is acting on Rn by linear transformations. I call it a semi-direct product. Okay. So this is a proper subgroup of the group of isometries of Rn. Right? I consider the I consider Riemannian symmetric space. I consider the symmetric space Rn. I get back what I get back is by this process On. Sorry, the pair is SON because I'm taking connected component. So out of Rn, the symmetric space Rn, I get the full isometric group, which is Rn semi-direct product SON. Now I consider the Riemannian symmetric pair out of this construction, and I consider as proper subgroup H of SON. I consider that group, and all this, my K is going to be H, and my inner everything is restricted to this setup, and the Riemannian symmetric space out of this that I'm going to obtain is Rn. Okay, so from a small setup, I'm going to obtain Rn as my symmetric space. But if I take the corresponding Riemannian symmetric pair, I'm going to obtain Rn full isometric group. Okay. So from a small, so when I start with a Riemannian symmetric space and consider, a symmetric space and consider the Riemannian symmetric pair, it is a maximal one. Okay, in some sense. But and this kind of thing happens only in the flat metric case. 5 more minutes. All right, I cannot start anything new, but let me just give some more examples of. So I wanted to give an example of a locally symmetric space which is not symmetric, and so this is an important example which I forgot to give. So let me end with that example. So I consider a Riemann surface G of genus at least 2. And this by uniformization theorem, this is covered by H, since it is genus G by 2. And So this is a biholomorphic. This is a holomorphic map. Okay, holomorphic covering. I have a metric here that you have seen. I bring down the metric here. With respect to that metric, this is a symmetric space. With respect to that metric, it is only locally symmetric space. It cannot be symmetric space. Because the isometric group of this is finite. Okay. Isometric group of this one is finite because isometric group modulo biholomorphisms, the bijective holomorphic maps of this. So why is this finite? Because this is finite. This is finite, and there is a theorem in complex analysis by Hurewitz which says that if I take a higher genus surfaces, compact surfaces, the number of biholomorphic maps is finite, 84 times G minus 1. Okay, so this is why this is a this is finite. Okay, this is a, I think it is an index, at most index 2 subgroup. I am not sure, but because this is finite, and this follows from this. And this is, PSL2R. And this happens to be biholomorphic automorphisms also. Biholomorphic automorphisms are like Mobius transformations. And this is PSL2R. They happen to be the connected component of the isometries of H. And this is why this is finite. And we know this is finite. So the isometric group of sigma G is finite. And a finite group cannot act on an infinite space transitively. So it cannot be symmetric. But it is a locally symmetric space because it is covered by a symmetric space. Okay. I'll end my that. What do I need to prove? I need to prove. So I am proving that this is not a symmetric space using a fact that on a symmetric space, the isometries act transitively. So I am proving that the group of isometries of this, I have a metric here coming from a metric upstairs or from H. The group of isometries is finite. And that follows from a bunch of facts, one of which is a celebrated theorem of Hurewitz, which says that if I take a compact surface of higher genus, greater or equal to 2, then the biholomorphic maps are at the most 84 times G minus 1. In particular, it is finite.